In this presentation, we continue to look at forces and we look at systems that are in equilibrium. So a system is said to be in equilibrium when it has no change in its motion, which means that it's either at rest or it's moving at a constant speed in a straight line. Both of these conditions are actually equivalent to equilibrium, and they both imply that there is no acceleration, which means that the net force that's acting on the system has to be equal to zero. So one example of something that we've seen previously is a system that's in equilibrium when it is hanging, so from a cord or a rope or something like that. And so in this particular example, I have a spring scale similar to something that you would see at the grocery store if you're going to weigh your bananas. And so if you hang a weight from that scale, you can actually read what the weight is on the scale. And the reason that you read the weight is because when you hang something from that scale, there's actually a tension that is holding up the object because it's hanging. In this case, it's like a stretching force because there's a spring in there. So it has to be true that if the system is in equilibrium, that the net force, the sum of the forces that are acting on the object, have to equal zero. So in my picture here, I have tension holding it up. I have the weight of the object, which is pulling it down, the force of gravity. And so if I add the tension to negative the weight because it's directed downward, I get that the tension has to be 3 newtons. Now this has to be true because the system is in equilibrium, so it's not accelerating, there's no change in motion, it's at rest. The two forces, the upward force has to equal the downward force of gravity. And I can see that my scale actually reads 3 newtons over here. This is a Newton scale. So we can often use the equilibrium rule to solve problems. So in this particular picture, I have a heavy crate. The crate weighs 100 newtons, and it's being pushed with a force of 50 newtons to the right, and it does not move. If it doesn't move, that means it's at rest, and its acceleration is 0. The question is there a frictional force acting on the crate, and if so, how much frictional force is there, and what direction does the frictional force act? The first thing is we know there has to be some other force acting on this crate because the crate is at rest. And if it's at rest and it has 0 acceleration, it has to have 0 force. So if there's a force acting to the right, there has to also be a force that is acting to the left. So there has to be something else present. We know that this is static friction because the block is not moving. There's no relative motion between the surface of the block and the ground or whatever the surface is that the block is sitting on. So there's definitely a static frictional force. So if the sum of the forces have to be equal to 0, then I can apply Newton's second law for the sum of the forces, and if I add them up, I have 50 newtons acting to the right, and I would add to it the forces that are acting to the left but negative, which is friction. They have to add up to 0, so that means that the frictional force has to be equal to 50 newtons. Now this is an interesting example because the static frictional force can actually change depending on the force that's applied. So if I had said that a force of 30 newtons was acting on the crate and the crate was not moving, I would go through the same process and the force that would have to be applied for friction would have to be 30 newtons. If the block is just sitting there and no force is applied, then the static frictional force is 0. So the amount of static friction on an object depends on how much force is applied. And eventually, if you apply enough force on this object, the object is going to start to move. And at that point, you've reached the most amount of static friction that you can have. And under those circumstances, the most static friction you can have is directly proportional to the coefficient of static friction and the normal force. So the second part of this question says, what is the coefficient of static friction if the crate is just on the verge of moving? So when this 50 Newton force is applied, this frictional force is actually the maximum amount of static friction that it can have, and it's on the verge of slipping. And we want to know what is the coefficient of static friction. So if I look at this picture again, I now have a maximum static frictional force of 50 newtons acting to the left. I have a force of 50 acting to the right. That's the applied force. Some of the forces are 0. And I know that the maximum amount of static friction depends on the coefficient of static friction and the normal force. So if I want to find out what is this coefficient of static friction, I can solve by dividing both sides by the normal force, and I know that the static frictional force divided by the normal force will tell me the coefficient of friction. So as of right now, I know what the I know what the frictional force is, it's 50, but I don't know what the normal force is. However, I do know that the crate weighs 100 newtons. So I have a force of gravity downward that's 100 newtons, and since the crate is not moving downwards, it's actually being supported by the ground, there has to also be an upward force of support force, or a normal force. And if I look at the fact that it's not moving in the vertical, the sum of the forces have to be equal to 0. So the upward normal force plus the downward force of gravity, which is negative, have to add up to 0, which tells me that the normal force has to equal the weight of the object. And so for the examples that we're going to do, most of the time the normal force will be equal to the weight of the object unless something is pushing on that surface. So now that I know the normal force and the maximum static frictional force, I can solve for the coefficient of static friction, be 50 newtons over 100, which is 0.5. The coefficients of static friction do not have units associated with them. They're just a number because I have newtons over newtons. And they are basically telling me that the coefficient of friction is telling me how easy it is to get this object in motion, right? It's going to be hard to get it in motion if it has a large coefficient of static friction, and this is basically the maximum amount of force you can apply before the crate actually starts to move. So if I applied 51 newtons, then the block would start to move, static friction would disappear, and it would be replaced with kinetic friction. So here's my crate again, and I've realized now that the crate is now in motion at a constant speed, so kinetic friction has taken over, if there is kinetic friction, in this case there is. So I apply a 40 Newton horizontal force on the crate. It's a 100 Newton crate. It causes it to move at a constant speed, and we want to know how much and in what direction does the frictional force act on the crate. So the fact that it's moving at a constant speed is very important because constant speed tells us that the system is in equilibrium, it has 0 acceleration, and therefore the net force has to be 0. So if the net force is 0, that means that there has to be a force acting in the opposite direction of the motion. So there is some kinetic friction that's acting in the opposite direction, and if the sum of the forces have to be 0, I can add up those forces, 40 newtons acting to the right, plus a negative frictional force acting to the left, and so my frictional force has to be 40 newtons. So there is a frictional force. In this case, because the object is moving at a constant speed, the frictional force has to equal the applied force. So sometimes this is a little bit confusing. So the idea is maybe you had to apply 50 newtons of force to actually get the object in motion, but once it's in motion, remember it's easier to keep it in motion than to get it in motion. So once it was in motion, you could reduce the force down to 40 newtons and it would just move at a constant speed. So we also want to know what is the coefficient of kinetic friction. So now we want to determine what the coefficient of kinetic friction is. So we know that the frictional force acting on the block is 40 newtons. It's moving at a constant speed, and so if we want to determine what the coefficient of kinetic friction is, we go back and we know the frictional force is equal to the coefficient of kinetic friction times the normal. We can solve for the coefficient of kinetic friction by dividing both sides by the normal force. So we know this frictional force is 40 newtons, but we don't know the normal force. But similar to the previous example, we have a force of gravity acting down, which is 100 newtons. The system is not moving in the vertical direction, so the forces have to be equal to each other. So the sum of the forces in the vertical direction have to be 0. So my normal force here is still 100 newtons as it was before. So now I can determine the coefficient of kinetic friction. I take the frictional force of 40 newtons, divide by the normal force, and I get 0.4. So one of the things I notice is that the coefficient of kinetic friction is less than the coefficient of static friction, assuming this was still the same crate. And so it takes less force to keep the object in motion than it did to start it in motion. Now it might seem like an odd question because you've got this force of 40 newtons and it's in motion. You've got friction that's 40 newtons. It's opposite the motion. So how did it get in motion? And so the idea would be that in order to get this crate in motion, you actually had to apply a force that was greater than 40 newtons. So maybe you had to apply that 50 newton force to get the crate in motion. Once it's in motion and kinetic friction takes over, it doesn't require as much force to keep it moving at a constant speed, so you can reduce the amount of force that you apply down to 40 and it will move at a constant speed. So we're looking at the block, after it's in motion and it's moving at a constant speed, but something had to actually get it in motion to start with, which was a slightly bigger force. Suppose that we had the same exact crate and it's in motion, and all of a sudden, instead of applying a force of 40 newtons, we apply a bigger force. We apply a force of 60 newtons. And what actually happens to this crate if the applied force is greater than the force of friction? So kinetic friction does not change based on how fast or slow the object is moving or based on the applied force. This is unlike the static frictional force. So that 40 newtons that we found for friction is still the same frictional force, except now I have this applied force. So what's going to happen is if there's more force being applied to the right, this object is going to actually accelerate now because there's a greater force applied to the right versus applied to the left. So we can look at the net force on the system, and we have 60 newtons to the right. We have a negative 40 newtons, we have 40 newtons to the left, which is negative, so there's a net force of 20 newtons on this object. If there's a net force, that automatically implies that there's going to be acceleration. And so we know that force is equal to mass times acceleration. I'd like to know what the acceleration is, but I need to know the mass. Well, if you know the weight of an object, which we do, we can always find the mass. So the mass is just the weight divided by gravity. So 100 newtons over gravity, which is 10 meters per second squared, gives us 10 kilograms. So I have a net force acting on this object of 20 because this force is bigger, mass of 10, so this object will accelerate at 2 meters per second squared. That means that every second that goes by, the speed of this object will increase by 2 meters per second every second. So we could also imagine, and I'm not going to do this problem, but what if this force here was actually less than 40? Maybe you're pushing it along and then all of a sudden you don't push with 40 newtons anymore, you only push with 20. And so what will happen is now there will actually be a net force to the left instead of to the right, and it will cause this object to slow down because the acceleration would be to the left and the motion of this object would be such that it would slow down. So that was a non-equilibrium problem. Another type of example that we might look at is equilibrium problems where we have multiple forces that are acting on an object. So here I have a painter and he's standing on a plank or a scaffold, and I have basically cords acting on both sides, and he's standing exactly in the center. And so we know that the reading of the scale on the left is 350 newtons, so the tension in this cord is 350. We also know that the plank has a weight of 450 newtons, and we want to know what does the scale on the right-hand side, scale 2, read, and what is the weight of the painter. So one of the things that's really important here is that the weight of the plank acts at the geometric center of the plank, which is exactly halfway between, which means that this weight of the plank would be evenly distributed between these two cords. The painter is also standing exactly in the center, and that's also important here. So that means that if he's in the center and the plank is exactly, the weight is acting in the center, that both of these scales have to read the same value. So if the left-hand scale read 350, then the right-hand scale would also have to read 350. And so this problem is a little deceiving. It seems like we don't have enough information, but the painter is in the center, which tells us that those two scales have to be the same value. But what is the weight of the painter? So the painter also, there's some force applied from the weight of the painter. We want to know how much does he actually weigh? Well, the system is in equilibrium, so the sum of the forces have to be equal to 0. So I can make my way across, and I can add up all the forces. I have a positive tension in a cord on the left, and I'm going to add it to the weight of the plank, which is acting down, so it's negative. And I'm going to add it to the weight of the painter, which is acting down, so that's negative. And then finally I get to the cord on the other side, which is holding it up, and that would be positive. So if I put those values in, the tension on the left is 350, the weight of the plank is 450 negative, weight of the painter, plus the tension on the right-hand side, which is positive, and they have to equal 0. So 350 and 350 is 700. Subtract 450, I get 250. And so the weight of the painter for these forces to add up to 0 has to be 250 newtons. So when you have something like this, you have to think about, the sum of the forces have to be 0, and how are the weights distributed? If it seems like you don't have enough information, then maybe both sides are actually the same value. Suppose that the painter, and we now know he weighs 250 newtons, moves over to one side, so he's not in the center. So what's going to happen is that the tension on the left-hand side is actually going to read a greater value. It's kind of like the person that was hanging from the rings, and depending on if they're holding on to one ring and releasing from the other ring, it's going to be a greater force. So some of the forces still have to be 0. I can go through that same process. I can make my way across. I have a positive tension holding up this plank here. I have the weight of the painter acting down, so it's negative. I have the weight of the plank acting down, so that's negative. And then I have the tension on the other side, which is acting up, and so that's positive. So I have 250 and 450, and those two values add up to 700. And then I have 500 here, so these are negative, so negative 700 plus a 500 should be a negative 200. There's a negative sign missing here. I apologize for that, but this should be negative 200 newtons. And so the tension on this side would be 200 newtons. And it should be less because there's more weight distributed on the left-hand side. All right, so here we go, one more. So we've got now two painters on my scaffold, or my plank, and I want to determine what is the tension over here on the right-hand scale. So I go through the same process. Some of the forces are 0. I make my way across. I have a positive force acting up, 600. I have a negative force acting down, 250. I have a negative plank force acting down, 450. I have a negative weight of the other painter, 300, plus the tension that's holding up on the other side. So if I add 600, so I've got, let's see, what do I have here? This is 250 and 450 is 700 plus another 300, that's 1,000. So negative 1,000 plus 600 is a negative 400. So the tension on the right-hand side has to be 400 newtons. So you can apply this to any example where you have an equilibrium and the sum of the forces are equal to 0.